What page are we on? So 3.5, related rates. I think it says chapter 3, page 9. Chapter 3, page 9. All right, I wish I had this filled in for you already, but it's not. Okay, can you write this down, please? Okay, guys, let's go. Okay, first step, yeah, draw a diagram part way through the motion, i.e. we're going to take a snapshot. We're going to draw a snapshot when we're solving these problems. So a problem like a lighthouse is, the light's going around, right? And it's like on the shore, what rate is it moving at a particular part? When the shore, so if you had a lighthouse, and there's a light going around, you have your shore here, right? So of course, we want to know, okay, how fast is it moving at a particular point on the shore? We'll look at specifically shore, those questions in trig. You can also deal with how fast the volume is changing. If we're, or the height is changing, when we're pouring something into a cone at a particular rate, how fast is the radius changing, or how fast is the height changing? Okay, so that's the type of problems we're going to deal with today. List all given. This is really going to be important because it's going to help you figure out if you need to eliminate a variable. So the given rates. List all given rates of changes. So those are your derivatives. And the one you're looking for. So if you're dealing with a problem that deals with a rectangular prism, they give you the rate of change of the volume. You want to find the rate of change of the height. They didn't give you any information about the length and width, and we have to somehow eliminate the variables because we only have two rates of changes that we're dealing with. And so we'll have to give you more information to eliminate those variables. Number 3, find the equation relating the variables. There is a variable that is not in the list. You need to remove it. So remove variables not in the list. So somehow, if you're going to have to remove something, you're going to need to find another equation. That was short for equation. Another equation that relates the variables and then substitute. Any constants should be put in before the derivative is taken. Because the derivative of a constant is 0. So if there is something that's constant, that's not changing, we're going to substitute that in before we derive. Oh, snapshot. Sorry. Okay, so then we are implicitly deriving. Implicitly derive. Because you're always deriving with respect to, I'm going to take a guess, with time, right? Because if you want the rate of change of something, it's all with respect to time. So how fast is the volume changing per second? How fast is the radius changing per second? How fast is your distance changing per second? So it's all with respect to time. So we're using implicit differentiation because our equations will not have time in them. Have other variables. Okay, 6 would be substitute the values and solve. Once we derive, we can actually sub in what we know. If any values are missing, go back to the original formula. Before derivative to calculate, and last we need sentence and units. Okay, so on your formula sheet, the green one, so you will get a yellow one later on in the year, the green formula sheet, the very front, there's a whole list of these formulas. So there's some in here. Does everyone have that down? 1 second. We're good to go? So there are in your formula sheet, there's no pictures, right? It's all compressed, and they are there. So you might want to have that out while you're doing your homework, so you're used to using your formula sheet when you get to your test. Okay, let's start with this basic example. So if x cubed y cubed equals 8, dx dt equals -3, dy dt, find dy dt when x equals 1. We don't need to eliminate any variables here because they give us dx dt, we're looking for dy dt, and x and y are the variables in the equation. Okay, so we want to find the change of x with respect to time, or sorry, change of y with respect to time. So our step is we're going to differentiate this equation first. How would I differentiate this? Oops. Product rule. Okay, so derivative of the first. 3x squared, y cubed, leave the second, times, because we're differentiating with respect to time and not x. Here, I'm going to do this. So 3x squared times derivative of x with respect to time, dx dt. Okay, times, so that's the derivative of the first, leave the second, y cubed. Because we're not differentiating with respect to x, we're differentiating with respect to time. So x is like now a function instead of a variable, because it's all with respect to time. To x prime, it's like x prime, but that's the derivative of the inside. Derivative of x with respect to time is dx dt. 2? No, because we did the power law already. 3x squared. Yeah, we're using the chain rule. Yeah. Okay, plus, leave the first. I know. Times the derivative of y cubed. So what with respect to time? The derivative of y cubed, first use power. 3y squared times the derivative of y with respect to time. Dy dt equals, what's the derivative of 8? 0. Okay. All right, so we are looking for dy dt. So let's make sure we know everything else. Do we know dx dt? Yes. Do we know x? Yes. Do we know y? No. Could we figure out what y is? Yep. So when x is 1, we just sub it into where? The first equation. So 1 cubed times y cubed equals 8. So y cubed is 8, meaning y is cubic root of 8, 2. You would never have, like, say it was like y squared. You would never have y, like, it would be positive over the 2. Oh, no. No. Okay, so let's plug in now what we know. 3 times x squared is, so x is 1. 1 squared times dx dt is -3 times y cubed, 2 cubed, plus 1 cubed times 3 times 2 squared times dy dt equals 0. So I'm just subbing everything I know. So we know dx dt is -3. Okay, it's 8 times -9, -72, plus 2 squared is 4 times 3, 12 dy dt equals 0. What's next? To move who? 72, yeah. So add 72 to the other side. And then divide by 12, which gives you 6. So it's positive 6, so that means it's increasing. It's increasing. So there's our solution. Because it's a positive, the y is increasing. Every second. In this case, it's just a general x cubed, like it's just a y. So if we graph this, we could actually get it alone, but it's as x is changing, how is y changing as x changes? So it's like a growing function with time. Okay, more common, you'll see problems like this. They're a lot more fun too. The length of a rectangle is decreasing at a rate of 1 centimeters per second. So what does that represent? So instead of L prime, because it's with respect to time, we're just going to write it as dl dt, and it's decreasing, so it's negative 1. And the width is increasing at a rate of 2. So that would be dw dt. Find the rate of change of the area at the moment when both lengths are 10 centimeters. So at the moment when we want to find what? Find the rate of change of the area, so that would be d a dt. So find d a dt when L and W equal 10. Yeah. So we have a rectangle. Basically what's happening with this rectangle, at that moment is square. So it starts off as a rectangle, and we know that our length is decreasing at 1 centimeter per second. Okay, that's our DLD. It's decreasing, and our width is growing. Oh, other way, this way. It's growing 2 centimeters per second. Okay. So is there a relationship between A, L, and W that we know of for a rectangle? Area equals length times width. And do we know the rate of change for everything, or are we looking for it? So we're looking for this guy. Do we know these two? The rate of change is for these two. Yeah, so we can go straight to deriving here. We don't have to get rid of a variable. Okay, derivative of area with respect to time. What's that? dA with respect to time is dA dt. What do we have to use here? Product rule. So derivative of the first, dl dt times the second plus, leave the first, derivative of the second, dw dt. All right, do we know everything to set? Yeah, we're good to go. So dA dt, what's dl dt? Negative 1 times our width at that moment, 10, plus the length of that moment, 10, and change of width with respect to time, 2. So negative 10 plus 20. 10 centimeters per second. Centimeters squared, sorry. So the area is growing. Is increasing at a rate of 1 centimeter squared per second. So most of the ones we're covering today, we don't have to do too much substitution. Tomorrow's going to be a little bit more intense. So, yeah. Good? Okay? No? Yeah? I like ladder questions. Yes. Okay. Oh, back? Lots. We'll get some more, you'll see, but you would use this a lot in like physics and engineering and that kind of stuff. When you're designing things, when you need something to drain faster than it's right, a sink, you need it to drain faster than the flow of the water, things like that. So how big would you need to make this and stuff? Okay, a 6-meter ladder is leaning against a wall, and its foot is sliding away from the wall at a speed of 1 meters per second. We're making its foot, its base. Okay, its base, its foot, the foot of the ladder. Okay, its feet are. It's only got one on it. That's why it's sliding. That's why it's sliding. Okay, anyways, at a speed of 1 meters per second, we're making an assumption about our wall. What's the assumption we always make about walls? A 90-degree, yeah. We're always making that assumption. Yeah. Okay, that would be a short wall. Okay, it's a pretty tall ladder, actually. Yeah, you need those for like roofs. Okay, a 6-meter ladder is leaning against, so let's draw this. And the foot is sliding away from the wall. So our foot here is sliding away. Now we need two variables for our vertical and horizontal. What are good two variables for vertical and horizontal? X and Y, is that okay? So what would be the 1 meters per second? What does that stand for? dx dt. Yeah. So is it increasing or decreasing? Is our value of x going to be increasing as it slides or decreasing? Increasing. So +1 meters per second. Find the rate at which the top of the ladder is falling when the foot of the ladder is 3 meters from the wall. Assume the wall and the floor are perpendicular. Okay, let's figure out what we're looking for. Find the rate at which the top of the ladder is falling. So we are looking for dy dt. It should be negative, correct. If it doesn't come out negative, you made a mistake. Okay, is there a relationship between x and y and 6 here? Good old Pythagorean Theorem. So x squared plus y squared equals c squared, or what's our c? 6. 6 squared. Okay, 6 squared. So x squared plus y squared equals 36. Okay, one thing you can do, because you don't always know you don't know if you need to figure something out, or right? Instead of doing our snapshot right away, we can derive first and then see if we need a snapshot. Okay, so we know the following information. I'm recording. Oh, yeah. That's why I'm wearing a camera. That's good. So let's go straight to deriving, and then we'll see if we have to figure out information, okay? So let's derive this with respect to times. The derivative of x squared, 2x times dx dt, derivative of the inside, plus 2y dy dt equals 0. All right. So we know we're looking for dy dt. We know dx dt. Do we know x and y at this point? could we figure it out? Yeah, so I need a little snapshot. So we want when, our snapshot is when x is equal to 3. Because it says when the foot of the ladder is 3 meters from the wall. So what if our x is 3? We need to figure out what who is. We are looking for dy dt. Right? So we have to derive it to get that. Right? So this is our unknown that we're looking for. Okay, we always, in math, we want to keep things as an exact value. So our y is equal to the square root of 6 squared minus 3 squared. 27, 36 minus 9. Could we simplify that guy? 3 root 3. Okay, so when x is 3, y is 3 root 3. So let's plug it into our equation now. So 2 times, what is x at this point when we want to find our dy dt? 3. Dx dt is 1 plus 2 times, what's our y? 3 root 3 times dy dt equals 0. So we have 6 plus 6 root 6. Oops, no, sorry. 6 root 3 times dy dt. Now what? Subtract 6. Then divide by 6 root 3. Unfortunately, we don't really want a radical on the bottom. Okay, so we can reduce the 6's. So we have dy dt negative 1 over root 3. How can I get rid of the radical on the bottom? Rationalize it, so what would it become? Negative root 3 over 3 meters per second. I don't know. It's just the way they like it in math. Somebody said we like it better. Okay. Sometimes it really doesn't make a difference, does it? Okay, so the rate, so we could say the ladder is what? Rising or falling? Falling at a rate of root 3 over 3 meters per second when x is 3. Or when the foot of the ladder is 3 meters from the base. Because it changes. The rate's going to change. Yeah. Yeah, whatever they say, their snapshot's always going to be that specific time they tell you. So in this case, when the ladder was 3, so that's our snapshot. Alrighty. One more. I love the baseball diamond. Did you want to try it on your own first? No, kind of not really. Alrighty. Okay, baseball. The Jays are supposed to do really good this year, but they lost yesterday. Yeah. It's supposed to be amazing.
Only like 1/622nd of the season.
Okay, a baseball diamond is in the shape of a square, right? Draw your diamonds. Guys, great. Oh, I have a diamond, sweet. But I need a diamond. But I need a diamond. Oh, that's not what I wanted. There you go. Okay, a baseball diamond is in the shape of a square, 27.4 meters on each side. Okay. Right, here's our diamonds. Good old baseball season's going to come soon. Yeah, I like it. Softball, not baseball. Okay, Mary starts running home from third. So where's third base? It's the third one. Okay, so here's first. We're going to make this second, this third, and this is home. Well, you can make it however you want. You could make home up here and third here if you really wanted to. Well, it depends on how you look at the diamonds. Okay. So, Mary's on third. Mary's on third. And she's running at a rate towards home, 2 meters per second.
That is so slow.
No, it's not. That's pretty fast. Mary has, like, Steve is the slower one. Okay, so Steve is starting, he's on home plate, and he's running towards first.
Yeah, that's not good. It's very slow.
Okay, anyways, 1 meters per second. Now we have to choose our variables. I use M and S. Oh, thank you, thank you. Okay, what?
It's Ortiz. He just hits.
Okay, anyways, how fast is the distance between them changing 5 seconds after they leave? How fast? Okay. Okay, so we can figure out their distances given the time. If you know she's moving 2 meters a second, 5 seconds later, how far did she travel? 10 meters, right? Okay, so what shape are we going to get? A triangle. We're going to get a triangle. Okay, it's going to get a triangle. So if we make a snapshot, guys, if we make a snapshot, what's the relationship between Mary and Steve? How are they being related? Somebody said the shape, triangle. So what is the relationship? Their distance? Okay, so we're relating their distances using which formula? Pythagorean Theorem. Okay, you're going to say. So if we call the distance between them, I don't know, D? D? Can I use, it doesn't matter. Okay, so this is Mary. So Mary, is her distance increasing or decreasing on this triangle? Decreasing. It's getting smaller relative to home. Triangle, right? This length is going to decrease. So we'll call her as dm dt. Okay, negative 2 meters per second. So m for Mary. And Steve, is his increasing or decreasing, this length here? Increasing, so this is ds dt. We'll leave it as a positive 1.5. Now we need to get a snapshot of what's happening. So it says, how fast is the distance changing between them? So what are we looking for in this case? What? The speed. So in the terms of this picture, what are we? d t. I shouldn't have used distance, right? We want the rate of change this is changing at, right, the distance between them. That's why they don't use d. Do you want to use a different letter? Whatever. Too many letters. It's keeping. So. D, whatever. Yeah, well. Okay. So let's look at our snapshot because you have to be very careful. They say, what is dt, or the distance between them, how fast that's changing when 5 seconds after they leave. So let's figure out what's going on. Copy. Okay, I need to try. So we're going to do our snapshot. Use like an iPad. Okay. Guys, seriously. Okay. So 5 seconds after they leave, let's look at Mary. How far did Mary travel? Remember, distance equals rate times time. So her rate was 2 meters per second times 5 seconds. So 10 meters she traveled. Now be very careful. Does that give us this length here? No. Well, it does indirectly. What is this measurement here? 17.4. So her distance from home is 17.4. Okay? Now, Steve, distance equals rate times time, Kate. So his rate is 1.5 meters per second times 5 seconds is what? 7.5. Does that actually represent how far he is away from home? Yes. So his S equals 7.5. Okay, the relationship. So this is our D value. How are we going to get that D value? Pythagorean Theorem. Okay, so D equals a square root of 17.4 squared plus 7.5 squared. What is this decimal? Because I want to keep it as, should we just leave it as a decimal? What's? Yeah, it's going to be ugly, isn't it? So let's go to 2 decimal places. What is it? 18.95 meters. Okay, so there's our snapshot. Am I losing you all? Yes? We're okay? All right, so what's the relationship between DM, this is our M, and this is our S? What's the relationship? Who squared? Oh yeah, M squared plus S squared equals D squared. Okay, let's derive this guy. We know the rate of change. Come on. We know the rate of change of M. We know the rate of change of S, and we're looking for the rate of change of D. So we want to leave them all in the equation. So let's derive the first guy. 2M dm dt plus equals 2D dd dt. Okay, what can we do to simplify this? There's something we can do to simplify it. Divide everybody by 2. Take out 2. That's prettier. And we're looking for who? dt, right? So we're M. Do you want to just go straight to subbing? Yeah, okay, let's sub. What's M? 17.4 meters. Right? Because that's at our snapshot. So she's 17.4 meters, 5 seconds away. She's 17.4 meters from home. Okay, her rate of change is -2 plus 7.5 is S. His rate of change, 1.5. No, it was in the question. Equals, D is 18.95 times dd dt. Okay, let's plug that into our calculators. I don't know. Can I just divide both sides by 18.5? Why? You can plug that into your calculator at once, right? Just have your invisi brackets here. Oh. Okay, so the distance between them is that's technically wrong. Okay, the distance between them, so is it increasing or decreasing? Decreasing. Distance between them. Okay, it's actually not a fraction because this was, right, this, we rounded this guy. Yeah, you did. Yeah, you. No, it was exactly 18.95. Yeah. The distance between them is decreasing at a rate of, wow, this took us a whole class, 1.24 meters per second. There's our sentence. Oh, that was fun, right? It's going to be a little bit of work in your homework. Oh, we still have lots of time. Okay. So homework. 3 to 9 and number 17 homework solutions are already online. So you're going to want to try practicing these. You will have a quiz tomorrow on it. Okay. Yeah, they are weird, but once you get practicing them, they're tough. They are tough. Like anytime we have application problems, they're always hard. Well,